Okay, I think we're live. I'd like to share this link real quick. Researching recursive descent parsing. Okay. Okay. So let me give a quick intro to the project again. There's a link in the description to the repository. What I'm trying to implement is a C compiler written in C that compiles to C. So effectively, at this point, it's just a parser or it's going to be a parser and a way to print the AST once we have it. And so it really doesn't do anything. That's the first step in the project. The first step is, write a C parser in C and output the AST as C code. So uh, understand the C program, but then directly translate it back into the C that was put in. And then once we have that, we can compile the compiler in itself. So it'll be self-hosted at that point, which is cool. The point is to get to a self-hosted compiler as quickly as possible. And I've tried it before. I've tried making like getting to a self-hosted compiler, and it's kind of a lot of work. So I'm trying this approach because I think it'll be quicker. And once we have a self-hosted compiler, then I can start adding language features and mutating the language away from just plain C and turn it into its own language. So that's the goal of this project. What I'm going to be doing today is sort of I began work on the parser. We have a lexer already, and it has tests. It works okay. And I began work on the parser in the last video. But since then, I've been thinking about how I've been going about it, and I think I'd like to take a slightly different approach. So I was reading up on recursive descent parsers, which is, I believe, the method I'm going to take for this. So the first thing we're going to do is just do a little bit of research about recursive descent parsers, because I don't really remember much about these. Okay, so it's a type of top-down parser. By top-down, we mean you specify a grammar in a way, and then if the grammar begins with like program, if the first non-terminal, the topmost non-terminal in the grammar is program, then you begin attempting to parse a program. If it was bottom up and like the C source code began with, you know, pound include, then like first we would parse, a pound include thing, and then you work your way up to eventually having a program, parsing the entire program. So that's bottom up. But this is a top-down parser algorithm. Okay, so you use a set of mutually recursive procedures, functions, or non-recursive equivalent. We're going to use recursion, where each procedure, each function implements one of the non-terminals of the grammar. Okay, so if we have a non-terminal called program, parse the entire program, there's going to be a function called parse the program. If there's a non-terminal called expression, then there's going to be a function called like parse expression. Okay, and then I believe a restriction on this type of parsing algorithm is that the grammar that you use cannot have left recursion in it. All grammars, okay, LLK grammars therefore exclude ambiguous grammars and all grammars that contain left recursion. So if you know what that is, we'll get to that a little bit later, but and ambiguous grammars have trouble or are difficult to parse, more difficult to parse with recursive descent parsers, but I think there are ways around that, so we're gonna go with that. Okay, and then this is the part that really made me rethink my approach. So they give an example grammar for PL0, I think, which I have no idea how that works, but down here, these last three non-terminals for expressions, this is like the standard example where you have, let me zoom in a little bit, where you have an expression, could be a positive or negative term, and then zero or more, plus or minuses separating terms. And then a term is like a factor followed by zero or more factors, and factors could have, multiplication and division. And a factor is either an identifier, like a variable lookup, a number, or a parenthesized expression. So that's the grammar that this example is based on. And then they give a C implementation of that grammar, which is pretty cool. So they're defining an enum for all these different types of symbols. I think this is like the tokenization. Yeah, this would be like the token types in the lexer. And they have a global tag called sim, which tells you which type of token you're encountering right now, that the lexer is looking at right now. And this is something I want to replicate. I think I do want to use a global variable. They also have this function called nextSim, which just mutates this symbol. It will just, advance to the next symbol. Okay, so there's an accept function which returns effectively a Boolean. You say, hey, I'm expecting this symbol, and if it does accept it, it'll advance and then return true, otherwise returns false. Expect, let's think about what this does. Expect takes in some symbol, so I expect like an if, the if keyword. If it's accepted, then return true, otherwise return an error. Okay, interesting. And return 0. So I think this would probably like crash the entire program if we're like, oh, we definitely need to see like the pound symbol here. Then you would use expect, the pound symbol, and then that should like throw an error message if it's not there. I think we'll see what this expect does, but okay. So factor, this is the lowest part, the deepest part of the grammar. So we should accept either an identifier, a number, or a left parenthesis, so a parenthesized expression down here. And there's also an error. And I believe this this program, the C program, does not build a syntax tree. So we have the additional task of writing this program, this parser, and as we're parsing, building a syntax tree. They are just leaving these branches blank, and they're just looking for like, does the text that we're parsing conform to this grammar? Return like true or false. So that's what these empty statements are for. So we're calling accept on ident first. Accept ident. So accept looks at this global symbol sim, and we're expecting an ident, an identifier. And if that's the case, advance the lexer and return true. Okay. And then we would go into the if and probably build some syntax tree node representing an identifier. And then same thing with number. Let's look at this branch though. So we're accepting left parenthesis. If we see the left parenthesis, then advance the symbol, the global sim variable. And then we need to parse an expression. And then after we parse an expression, we will expect an R paren. And let me, oh, and this is expect, not accept. Okay, right, because if we're inside of this branch, we know there must be a closing parenthesis. So if there's not a closing parenthesis, expect will throw an error. And I imagine this ought to be like some kind of error recovery or else just like quitting the entire program. Because we're going to like continue if, oh, well, we'll think about that a little bit later. Okay, and then if we were looking for a factor and none of these, worked, then we're going to throw an error. Throw an error and do next sim. That's interesting. Throw an error and do next sim. I guess this is some kind of error recovery where, like ideally you would have like line and column information in this error message and say, hey, we were expecting a factor, couldn't find a factor. We're going to continue parsing though. Okay, that's interesting. I imagine there's like several ways to do this. Okay. And then a term is, okay, is you need to parse a factor, which we just looked at, parse a factor. And then there's a while loop here. Okay, while the symbol is either times or slash, so either multiplication or division, then advance the symbol, and then parse a factor. Okay, this is interesting because we're going to have to remember to advance to the next symbol, like at sort of weird locations. I sort of wish there was a better way to do this, but I don't know, it's almost like maybe if we put this as like, if you threw parentheses around this condition, this OR condition, and then did and next symbol in the while loop, that would almost make more sense to me. But okay, so we continually parse factors. And again, this code does not show building a syntax tree. For us, the whole point of our program is we need to build a syntax tree. So, and then expression, okay, so optionally it starts with plus or minus. That's unary plus, unary minus. And we'll skip past that. And in our program, I'm not sure we're going to implement unary plus minus because we don't really need to at this point. But if we were, we would also have to build, we'd have to modify the AST node that we're going to be building here to reflect the fact that it's a unary plus or minus expression. And then parse a term, and then parse 0 or more pluses and minuses followed by terms. Okay. Yeah, so that's how you parse an expression. Okay, and they go on to the entire grammar, starts out as program. A program is a block, and a block could be like const, ident, equals, blah, blah, blah. Procedure and statements, conditions. I'm going to ignore all of this though because I think I can figure it out, figure out where to go from here. So let's now go back to our code and think about how we need to change things to fit this model. So in the Lexer, this is our Lexol input example program, which just sort of takes in some source text and like prints out all the tokens one after another. And And this is the call to our lexer. It's inside of a while loop. And lex returns false when it gets to the end of the file. Okay. And it exits early. This is the end of the lex function. It exits early with an error message if there's some token that it doesn't recognize. Okay, so we're repeatedly calling lex, and then we're getting the output token type. So this variable here, which I've initialized as garbage, actually, okay, yeah, that's fine. This is analogous to sim in this example. Over here, this is like sim. Okay, that's like sim. Token is like some extra information. It's the string representation of the token that we're looking at, if that's relevant. So if we're parsing, if we tokenize an identifier, then token will point to the string that contains the text of that identifier. So if it's, you know, if we were parsing this, the identifier would be this. So token would point to a string that contains the text lexol input. And what I'm doing here is we pass in the original input, which is here, and then we pass in effectively a mutable reference to input, which once lex tokenizes a token, it will advance, it will set this out parameter to the updated position in the source text. And we are using the same variable input in both cases because it just goes in here and then it's going to mutate that. Which actually, I don't think this is valid Rust code if you were to write this in Rust, because you have an immutable reference here, and then a mutable reference here. Okay, so this is already a little bit sketchy. I believe the reason I was doing it this way is because I was essentially working off of my experience with parser combinators, where you return in Rust, a parser, or in this case a lexer, returns a result of either or I guess essentially it's an option where the one thing is a string, which is the updated position, and you usually return some value, but I guess we can forget about that for now. So I would like to be able to return something like this. Which honestly, I suppose I could, because if I just returned a pointer, then it has optionality built in, because we could like check if it's null. Huh. Okay, but that's how you do it with parser combinators. You return like an optional string, which is the updated position in the text. But the way that they're doing their parser in this example, they have like a global symbol. They've declared some global function that mutates some hidden input state. So it's like there's probably also like char pointer input as a global variable that next sim advances internally. Okay. Okay, interesting. So I think I do want to like change it to be like this example, just because I'm feeling like this is getting complicated and I'd rather have like a roadmap for where I want to go. So maybe we should go down below all of these and we should say enum token tag sim. So that will be the, I don't know, maybe I should call this token tag. And then a char pointer called token, and we should document these. The token tag of the current token. And this will be the text of the current token if relevant. So for like keywords and stuff like const, struct enum union, I'm not, like, we know what the text is, so I don't set that just because it's kind of annoying. We also need a character pointer called input. The source text, a pointer to the current location in the source, in the source code that we're lexing. Okay, and this one, and this input is going to be updated. Is going to be updated by the function next token. I don't know, maybe we should call it like advance. Next advance, I don't know. Next token. I think that's good. Although that sort of implies that like it's going to return the next token. So I think I'd rather call it advance lexer. Okay. And I think if we're doing it like this, so I'm tempted to write bool here, in the same way that my current lex function returns a boolean, and it says, okay, it'll return false if we're at the end of the input. I think I would rather keep this void and just add a token, which is end of input. Token end of input. So in the when I was taking classes and compilers, and I think in the textbook we used, they would use like dollar here as like the symbol for the end of the input. Let me put that up here as documentation. They would use the dollar sign as like the symbol for the end of the input. The end of the input has been reached. Okay. That way this can be void, and it'll be the parser's problem to check that we're not at the end of the input, or to check that, at the end of the program, at the end of a valid program, we encounter the end of input token. Okay. So how do we write this? Advanced lexer. let's actually make this a prototype and then go down below Lex. Lex all input. This is below Lex. And we need to assume that the global variable input has been set. So we're calling Lex on input. The out token type will be a reference to the global variable token tag. The out token will be a reference to the global variable token. And then the updated input will be, we need to pass in input like this. So this returns a Boolean result. Which we're no longer using. That's interesting. Okay. I don't know how to throw away the value of a result. Like in Rust, you do underscore so that the compiler doesn't complain at you. Oh well, I don't have those warnings turned on anyway, so let's just forget about it. Okay, I think this actually might be all we need in this function, advanced lexer. Mutates global state of the lexer. So the reason I'm allowing myself to use global variables, one, is because it's closer to this example, and since I've never really written a recursive descent parser before, I'd like to stick to this example fairly closely. And secondly, I think in C it's okay to use global variables because you sort of treat this like entire file as like a module or like an instance almost. Sometimes it's kind of like a singleton instance because we're not spawning a process or anything, and there can only be one instance of this file. But I think that's okay. So I think this approach is like, fits in with C a little bit better. So that's why I'm allowing it. Okay, and we can change this later if we don't like the approach, but I want to just get it working right now. Maybe I'll just delete all that. So we mutate input through this process. I think I do need to change. Yes, allow white space. I think what I should do is we'll do allow white space, and then if input equals the null character, if we're at the end of the input, then we need to set the out token type to token end of input. I guess that should come first. and then return false because we're at the end of the input. Yeah, returns false at the end of the input. So I'm trying not to like change the behavior of this function too much. We'll just return an extra token. Okay. So now the end of input token is being used. Okay. All right. Advance the Lexer. Yeah. I'm a little concerned that some of these functions are going to break. Hopefully the names are like shadowed. So for instance, if we just go up here, yeah, to like, where is expect ident, out ident, okay, that's fine. Okay, so for instance, input. This is the name of a global variable. Hopefully it gets shadowed by this. Like, I would be very upset if that was not a feature in C. Okay. Maybe we should, maybe I should call this Lexer Advance. And I'm going to sort of namespace this. Void Lexer set input to character pointer new input. And then we're going to say the global variable input equals new input. That way we're sort of building up an API here. Enum token tag Lexer get toke tag. I mean, that's going to be annoying to write everywhere. I'd rather just use the global variables directly. Okay. Okay. How do I test the Lexer? Let's go back to the main file, which is being taken over by the parsing code right now. Main, okay, instead of this, we're going to say test Lexer. And let's make sure that the old code still works. Yes, it does. So it's still printing end of input down here. This is not really very relevant. Maybe we should turn this into a do while. I don't need to look at the return value of this. Do while output token type is not equal to token end of input. Let's try this. So we should see token end of input at the very end. Oh dear, okay. No, we do not. Infinite loop somehow. Token close brace. While out token type is not equal to token end of input. So if it is equal to if it is equal to token end of input, then we break out of the loop, right? So can I scroll up? Let's run it again. /paracc.exe. I want to like catch it before it goes into this close brace thing. There we go. Okay. So we're going all the way down, literal string, semicolon, and then close brace. Literal string, semicolon, close brace. And then we get stuck in a loop. So what's going on? Token end of input. Find all references. So here's where it's defined. And here's where it's used. If the input is at the end of the string, if the input is pointing to the empty character, then set this. Okay, we're not setting this somehow. So let me check inside of allow white space. If new input, if the end of new input is the null character, we return something. Allow white space. Oh, is that inside of an if condition? So that returns allow white space, returns true if it's at the end of the input. Okay. If this returns true, we're at the end of the input. And we ought to do this. Set the output token type. Okay, let's try that. Yes, okay, there we go. Token end of input. All right. So what have we changed? Add new API for lexing. Okay. I think I'm just about out of time. I'd like to cut this short so that these videos aren't too long. But let's go back in and try to use the new API for something simple to parse. So parsing a literal int. Okay. We don't need the input anymore, actually. So let's rewrite this function. We'll save the old version for now. we'll call this new. We do not need the input because that's going to be global. We do need an out parameter. We don't need the new input because that's also global. We don't need either of these because those are global. We don't need to call lex. Let's go look at how they accept a number. So they have a function called accept. Maybe we need to add this to our parser, accept and expect, or to our lexer. Yeah, let's do that. Lexer accept a token, an enum token tag, and this returns a boolean. Accept and expect, yeah, they return ints, but I'm using booleans. And we just check the global token tag and then call advance. Okay, so if, just copying and pasting, if token tag equals tag, then lexer advance, and then return true. So it worked. Otherwise, return false. Okay, and then expect, it's going to be very similar. Lexer expect enum token tag. If lexer accept tag is true, then return true, otherwise throw an error. Return true, else the error, I don't know. Unexpected token. Okay, we can make this better. Return false. Lexer expect. Okay, now let's, now let's go back to, I might as well commit this, add expect and accept functions to lexer. And then let's go back here. And inside of our new parse expression literal int function, we're going to return accept number, bool results. I'm not sure. If accept lexer accept, and then the name of a token, toke literal int, then we're going to do all this. Otherwise return false. Token, yes, is a global variable now. So that actually works. And then expression literal int. Do we need to advance the lexer at this point? Accept ident. No, because accept advances it for us, right? Lexer accept advances on our behalf. Okay. I wonder if I could add that as documentation. Advances Lexer input if the token tag matches. Okay. And this one does not. Am I correct? No, it does because it calls accept. So they both actually advance on our behalf. So if you call accept or expect, you do not have to advance. You do not have to advance the input yourself. Okay. Okay. I am supposed to. I actually okay, and I don't need to return. I actually don't need to return anything. So this can be void. Ooh. Okay. I'd sort of like to test this out. Test new parsing method. Let's set Lexer set input to let's add some spaces and a new line character and then -1, 2, 3, 4. And then, I don't know, some more spaces and whatever. Okay. So we set the input, and then we want to call parse expression literal int new, and I need to pass it an out parameter. I mean, at this point, I could probably just be returning these. That would be convenient. Struct expr pointer, just a regular pointer expr, and then pass it by reference expr. And then display expression to standard out expr. Okay, let's run this function and see if it works. So we're going to go down to main, test new parsing method. Let's clear the input, and we should see the int come out. Okay, we got nothing. Is that our fault? It's definitely my fault, but test new parsing method. Is it the case that I should have... Let's make it simpler. Let's make the input really simple. Still nothing. Let's try printing something. Printf done test. Nothing. Let's print something before. Okay, yeah, so we print out something ahead of time. So we're getting in here, and then there's some problem in here. Parse literal int new. Lexer accept token literal int. Yeah, I mean, that makes sense. HY token expr literal int. Let's print something here. Printf here. Are we getting inside of the if expression? No, we're not. Okay, so Lexer accept. There's something wrong here. Token tag. If token tag equals... it's possible. Oh, okay. I think I need to call Lexer advance at the very beginning. So I think what I would like to do is go to the, go here, Lexer set input, and let's make a function called Lexer init, in which we call Lexer set input to new input, and we call Lexer advance. Because we need to initialize the token and token tag before using them. So now we go back here, and instead of Lexer set input, I'm going to use Lexer init. Let's see if that fixes the problem. Yes. Done with the test. Okay, it almost fixes the problem, except that the number we're getting out from token is 0 instead of -1, 2, 3, 4. Interesting. A to Y token. This could be because token is not being initialized. Token in Lexer advance. Yes, so this is the global variable. The text of the current token. And we're passing in a pointer to that. Yeah, out token is a pointer to a pointer. That makes sense because it's an output variable. Lex literal int takes the out token. Takes the out token. And we're copying that value in to out token. We're allowing a negative sign up front. That should be okay. And then down in Lexer Advance, we're passing in a reference to the global token. The text of the current token if relevant. So yes, this token is correct. Let's print out what token points to. Printf token equals %s token. Let's print that out. token, okay, it actually points to the next thing. Interesting. Okay. So it's pointing to this thing because we've already advanced past. So somehow I need to store like the previous token. Oh dear. Um, hmm. Okay, I think I need to end the stream here, just because I want to keep this to be around 45 minutes. I think we're beyond that already, but um, I'll have to rethink this approach a little bit inside the Lexer. But in terms of this new way of doing the parsing, I like this a lot more than this. So here I had to keep track of some internal state and sort of thread the input state through the Lexer all the time. Up here, I don't have to worry about that at all. All I have to do is, call this on an expected token, and I don't even have to return anything, which is nice. You just say, okay, if it works, it works. Otherwise, we're gonna like continue. Um, okay. So I think that's where we'll end it for now, and maybe I'll do some debugging off camera to figure out what I need to do next. All right.